Good afternoon and welcome to the afternoon session. We will begin this session by a talk by Professor Bedanga Mahanti from NICER on India, heavy ion physics. It's a 20 minutes talk plus 5 minutes discussion. Bedanga.
Okay, a very good afternoon to all of you, and thanks to the organizers for giving this opportunity to talk about the status of heavy ion physics in India and its future directions. What we do using relativistic heavy ion collisions are studying emergent properties of strong interactions. This is a time evolution of relativistic heavy ion collisions. And as you can see that the system is femtoscale in time and also in size. That makes measurements and interpreting the physics quite challenging. What physics that we do is encapsulated in this phase diagram of strong interaction. X-axis is baryonic chemical potential and y-axis is the temperature. There is a high temperature density phase where quark and gluons are deconfined and chiral symmetry is restored. There is a low temperature density phase where quark and gluons are confined into hadrons and chiral symmetry is broken. We would like to produce this state in laboratory and study its properties. On the phase diagram, if you look at this point here, the white point here, it is the QCD critical point. It is a landmark point in this phase diagram. Why? Because on top of it is the deconfined phase of quark and gluons. Below it is the confined phase. On the right of it is first order phase transition and left of it is crossover. If we manage to locate, or if it at all it exists on this phase diagram, then this phase diagram will become a reality. The Indian groups have been involved dominantly in CERN and BNL-based experiments. And the participation started in early 1990s in WA93, then WA98, STAR in BNL, ALICE at CERN. Our main detectors try to detect photons and muons, but the major contributions have been in detectors and electronics, physics analysis, and theory. Theory part is very crucial in order to interpret and understand our data and to also suggest observables. The community is also growing. We started with a school in 1989, as far as I remember. I had not joined this community. And then we have our flagship international event or the conference, which is ICP QGP every 4 to 5 years. The next one is coming up in Puri, 5th February next year. So the community is also growing. Now coming to what have we learned from heavy ion physics. First, I will start with what does the first principle QCD calculations on lattice tell us. It tells us that at a temperature of about 155 MeV, this transition from a confined to a deconfined stage will take place. So that is the temperature we have to achieve in the laboratory. That corresponds to about 10 to the power 12 Kelvin. And it is the temperature which existed if you follow the Big Bang model in a microsecond-old universe. It's also interesting to note that among the transitions which took place in the universe, this has the right temperature or energy scales which can be probed in the current day accelerator domain. You can actually think of producing this state of matter. On this slide, I saw the importance of having close theory and experiment collaborations. The red points are experimental measurements, and these black points are theory calculations, both corresponding to measuring susceptibilities of baryon number. Experiment plotted as a function of collision energy, and you could translate it to temperature, where you can use theory to calculate. And there is excellent agreement between the data and the measurement. Have we reached temperatures above this? Well, one way to look at it is to measure photons. Photons which are coming from, these are direct photons or single photons which are coming from quark and gluon interactions. This is the distributions, yields of these direct photons as a function of transverse momentum. It is exponential in shape, thermal, and the slope gives us an idea about the temperature, which is well above the critical temperature for QGP formation. Another temperature which we can extract is use the particle yields and try to fit it to a statistical thermal model with temperature as a parameter. And we fit the yields of various kind of hadrons, from pions, kaons to nuclei. The dots are data points, the lines are theory, excellent agreement, and the temperature turns out to be pretty close to the transition temperature. So hadronization happens very close to the transition temperature. So it seems we have reached that temperature, but have we formed quark-gluon plasma? In order to show signatures of quark-gluon plasma, we have to show that the measurements require the relevant degrees of freedom are quark and gluons. They show collectivity, and there should be some device screening-like effect. There are a lot of interesting measurements at RIC and LHC which probe this aspect, and I'm showing two such measurements. In here, we have plotted in the y-axis is just the ratio of the momentum distribution of hadrons in nucleus-nucleus collisions to proton-proton collisions. If nucleus-nucleus collision is a simple superposition of proton-proton collisions, this should be unity. You see a suppression. This is associated with a phenomena called jet quenching. The quark and gluon jets are quenched in a colored medium. So the relevant degrees of freedom to understand these measurements are free system of quark and gluons. Here is again a strangeness production in heavy ion collisions relative to proton-proton collisions. And you see it's above 1, so strangeness production is enhanced. X-axis is some proxy of impact parameter of the collision. Let's focus on these red points. These are 5 mesons, which is a strange hadron, SNS bar, but its net strangeness is 0. So it cannot be canonically suppressed. As a result, this enhancement is mostly coming from the denominator, since phi is not canonically suppressed. So this can also be explained only if you invoke quark and gluon degrees of freedom. Do we have collectivity? This plot shows a measure of collectivity in y-axis as a function of transverse kinetic energy, where x and y-axis are divided by number of constituent quarks, 2 for mesons and 3 for baryons. Several different kinds of hadrons, differing in charge, mass, baryons, mesons, they all seem to line up in one curve. That shows that this collectivity has some common origin, and it is from quark and gluon phase. So it's partonic collectivity. Now, what about device screening? We tried to measure yields of JEPSI, again, in heavy ion collisions relative to PP collisions, and you see a suppression. JEPSI is a CC bar bound meson, and this suppression can arise if it is device screened by presence of other quarks. So we have seen all these 3 features, and quark-gluon plasma is formed in the laboratory. Now, once we have the quark-gluon plasma, and specifically at LHC, where its duration can be long because we have higher energy density, we can study its properties. So what are the properties so far we have looked at? Here again, you need a very close collaboration with theory to confront with or match with the experimental data and obtain these properties. The first one is shear viscosity to entropy density. You compare viscous hydrodynamic calculations with experimental data of collectivity, and you find that it is these values. Lowest compared to any other known fluid. And that's why the quark-gluon plasma is called as a perfect fluid. We have also extracted bulk viscosity. The uncertainties are large. We have extracted, got an idea about diffusion coefficient. Here it is presented in a dimensionless quantity as a function of temperature. Here are lattice QCD calculations, and the uncertainties are large. It seems that the heavy quark perform Brownian motions in this thermal bath of light quarks. When we collide two heavy ions, there are 2 major initial conditions. One is large magnetic field, and large angular momentum is imparted to the system. That could cause polarization of the quark-gluon plasma. We have measured the polarization through hyperons in percentage as a function of collision energy, and there are finite values. If you take the average value of the polarization and assume that the entirety is converted to thermal vorticity, it turns out to be 10 to the power 21 rotations per second, the most vertical fluid produced in the laboratory. We have also got an idea of opacity in terms of a transport parameter, transport jet parameter Q hat. It turns out to be of the order of 2 GeV square per Fermi, indicating a very dense medium has been formed. So these are what the properties of quark-gluon plasma we have studied. Now, what is the status of the phase diagram? I come back to this temperature versus baryonic chemical potential. At close to 0 baryonic chemical potential, the transition temperature is around 155 MeV. Hadronization is close to that. And it's a crossover. That is, QCD calculations suggest it's a crossover. But do we have any experimental evidence that the system is thermal? Now, we have tried to probe the multiplicity distribution of net baryons up to 4th order and found that thermal models are able to explain 1st order, 2nd order, 3rd order, 4th order data very well for below 140 MeV. So system appears to be thermal at least up to 39 GeV from the measurements and theory. What about the critical point? Theory says that if you look at the 4th order fluctuations of net proton distribution as a function of collision energy, it should show a non-monotonic variation. We see a sort of non-monotonic variation at 3 sigma level. Errors are large. We have collected high statistics data last year, and that will reveal the true picture. But what we have done also is measured in fixed target mode at 3 GeV and found that this system is hadronic in nature. It sort of puts a region from the experimental perspective. If critical point exists, it has to be between this part of the mu b, x-axis of the phase diagram. It's between somewhere 200 to 750 if a QCD critical point exists on the phase diagram. Now, let me come to specific contributions from Indian group. This is selected results, and we started with first observation of collectivity in WA93, and then went on to measure partonic collectivity, disoriented chiral condensates, made substantial contributions towards phase diagram of QCD, discovery of anti-helium. Through our photon multiplicity measurement, we observed an unique longitudinal scaling associated with limiting fragmentation. We also saw evidence of spin orbital angular momentum interactions and rescattering effects. As I said, the theory plays a very crucial role in interpreting the data. And there has been very, very major contribution from the Indian theory groups. And this is only some selected results, starting from lattice QCD, where diffusion coefficient calculations, as you saw when I showed the comparison plots, or where is the likely position of the QCD critical point, pioneering work in electromagnetic probes of quark-gluon plasma, equation of state, heavy quark propagation, and currently people are actively working on developing relativistic hydrodynamics, viscous hydrodynamics with magnetic field and spin. These are ongoing developments. This month itself, I think colleagues from India with other collaborators have shown how to put together relativistic spin magnetohydrodynamics framework in place. It's a starting point, and this would be best to understand the data. Now coming to future, the relativistic heavy ion collider program, the STAR experiment, will take data up to 2025. And then, of course, the data will be available for physics analysis. We have CBM experiment in FAIR. I think that Professor Chattopadhyay will discuss in detail. We also want to participate in the electron ion collider program, which will start possibly taking data in 2032-34. Currently, we are working with the ALICE experiment at LHC, gearing up our detectors and to cope with the high luminosity, which we will be sampling, as well as improving on pointing resolution, where we will try to focus on heavy flavor measurements to get better handles on transport properties of quark-gluon plasma, reduce the error bars, and understand its dynamics better. So in the what are we involved currently is a forward calorimeter effort, which is a sampling calorimeter of silicon and tungsten. And the physics focus is to understand the distribution, the pattern distributions inside the nucleon and the nucleus. India is a major contributor to this detector effort. In near future, we want to participate in ALICE-3. ALICE-3 will be a complete overhaul of the current ALICE detector. It will have layers of advanced silicon detectors. In fact, it would have wafer-size CMOS active pixel sensors, which will go down to thicknesses of about 30 micrometers, and they can be wrapped in cylindrical way so that the material budget is less. And there we are going to address specifically chiral symmetry restoration and, of course, transport properties through heavy quark measurements. We have already taken data in the beam energy scan program, which will shrink these error bars to this level. And this will give us clearer idea about the phase diagram of quantum chromodynamics in the STAR program at RIC. In the electron-ion collider program, it is a unique facility which provides us collision of electrons with polarized protons and electrons with nuclei. It will address some very interesting physics questions, which I will come to in shortly. But there is already a starting of an experiment collaboration forming called as EPIC. And several Indian groups are associated with it, both from theory and experiment. The timeline, as I said, is somewhere between 2032 and 2034. Now, coming to all that I discussed has been put together in this mega science vision document of nuclear physics in 2035. There are 3 sub areas, the one on heavy ions, then low energy nuclear physics and plasma physics. These are the working group members. A subset of them form the drafting group members who have been meeting regularly for last 1.5 years every week to come bring this document, which will be discussed in detail by Professor Amal Dighe. And there are regular consultations with the working group. We obtain inputs from individuals, institute, facilities, collaborations, both theory and experiment. And we prepared the first draft, which was circulated among about 4,000 scientific members across various areas, and inputs were received. Some about 60 written inputs were received, and they were incorporated in a revised draft, which was then discussed by a team of national and international experts. There also we got some detailed 9 comments, and those were incorporated. And the next version of the draft was discussed with the principal scientific advisor. We, in this course of preparation, consulted the STIP document, the past vision document, and long-range plans in US and Europe. I will only tell about the heavy ion part recommendations which is proposed in the draft. This has got to do with this phase diagram of QCD. I again come back to it, temperature versus baryonic chemical potential. The way to access it experimentally is by changing collision energy, you change the X and Y and X axis. LHC is around here, FAIR is somewhere here, and RIC in between. So in order to get this phase diagram, we need to take data at LHC, RIC, and FAIR. And that is the recommendation from this community. And especially in the high density baryonic matter regime of CBM. We, of course, would like to participate in the electron-ion collider experiment, not only to address these fundamental questions, but to understand the initial conditions of heavy ions which we are colliding. Now, one other aspect I just want to mention is we have a detailed discussion on industry participation in mega science project. There is in the annexure, there is a list of industries which have contributed to this project. What is heartening to know is that the Indian companies are going beyond that and getting some work from other than experiments. At CERN, for example, these are some of the few examples. So that is a positive trend in that direction from Chennai, Vadodara, Nasik, all places of India, Lucknow, Kolkata, and they are contributing to it. We feel that allowing industry to be directly part of mega science project will be a good thing. Also, we should develop avenues where UG, PhD, and postdoc get industrial experience in industrial setting. That would help them in future, and perhaps supplement existing grant for high risk, high gain research in order to develop some generic technology. There are also features which we have presented in the document, which is cutting across the mega science areas. For example, computing is one where we have recommended petaflop level machines for centers and hundreds of petabytes of data storage and good connectivity. Another important aspect is the National Detector Development Training Center. This is very crucial for our participation in any mega science project. And I think this is true for all mega science projects, not only nuclear physics or even not only high energy physics. We should have specific human resource development programs, and outreach is an important component where India has last year joined International Particle Physics Outreach Group. We also have given a timeline. This is so as to see how we have a finite number of people and resources, so how these are spanned out. Keeping in mind that we will be looking at the physics possibility, we will be looking at the upgrades and also planning for future experiments. These are the set of experiments, and they seem to be nicely phased time-wise. So I'll come towards the end. What we are doing is towards a complete test of QCD as a theory. What I mean by that, we have the standard model with Higgs origin of mass. We have tested QCD at perturbative regime excellently. The theory works. This is jet cross-section with jet PT, several orders of magnitude in PT, X and Y axis. We have also tested QCD in the non-perturbative regime at ground state. Masses of hadrons are very well explained with less than 5% accuracy. We have gone one step ahead, non-perturbative regime at finite temperature. There seems to be good agreement with QCD and the experiment, and we are laying out the phase diagram of QCD. We will take all this to one more level if we participate in, we have already started participating in the Electron Ion Collider program, where the four important questions, some of the four important questions are, how do quark and gluons form nuclei? How does proton get its spin, gets its mass, and what is the nature of dense gluon matter? We will perhaps be making a transition from temperature versus baryonic chemical potential to parton density related to 1 by x, and resolution, which is related to momentum transfer square, q square. And we'll see what emergent properties QCD lead us to in this facility. That is all. I would like to thank all the experimental collaborations, the theory colleagues, the drafting and working group members of the Mega Science Vision exercise. And I would like to point out that this month, Alice released a review paper which encompasses the last 10 years of physics which the detector has carried out. Thank you very much.
Thank you very much, Bedanga, for this comprehensive review. And talk is open for questions, comments. Yes, please.
Bedang, I was curious, this phase diagram at one point you said where the ALICE is running and where the RIC is and CBM is. Is there any problem that ALICE was on the top corner, right, left side? That's what, yeah, around 1. That's what you said where it's running. Can it not tune its things to run where the RIC is running? Is it not possible?
Yeah. So how is the question then is how is center of mass energy related to this X and Y axis of the phase diagram? So if you go increasing the collision energy, then you go to higher temperature and lower baryonic chemical potential. If you go to lower collision energy, then it is higher baryon density region and moderate temperature. So that is how it's linked. RIC beam energy scan actually does that, goes from 200 to 7.7. And LHC then covers from 2.76 to 5 TeV. And CBM will then take over from 11 to, I think, 3 or 3 GeV, which Suhasita will say.
So another quick question is, apart from the critical point, understanding its property, the next big questions is what you put the 4 questions in the last slide. Is that correct?
That is, of course, fundamental questions.
Fundamental questions in future to answer. Thank you.
Yeah, so you mentioned that you plan to study chiral restoration with Alice in the future, if I understand correctly. So what's the observable there?
It is looking at the rho and A1 chiral partners, whether their spectral functions meet or they vanish. But we have to take it with some caveat that we need to, the theory tells us that it's a 10% change, which we will see in experimental observable. So all efforts are there to get the backgrounds and the reconstructions done so that we can see a 10% different with and without restoration. So I just indicated it in one of the plots here, but oh, it's taking time.
So how do you see the changes in the masses?
We will reconstruct the dileptons and have an invariant mass of the dileptons.
Yes, I understand how you can measure the rho mass. But
yeah.
And the A1, you just assume it's not changed?
Yeah, so we have these spectral functions, which comes from theory. We will have our measurements and then confront it to the data to see if we see any changes.
Okay, I think we should perhaps move on and call on Professor Chattopadhyay for the next talk, India and Fair.
This is yours? Yeah. So you can remove the tag. You can remove this tag. This is a pointer forward, backward, and this.
Good afternoon, everybody. I'm going to present before you an upcoming accelerator center in Germany at Darmstadt and Indian involvement. Now, I will start where essentially Vedango continued. This is the diagram which I think everybody knows, that this is a Big Bang and this is where we are today. And this is the time passes by and this is the energy. Now, I will request you to draw your attention at this point, which is 10 to the minus 5 seconds, where it says nucleons form. So if you draw an imaginary line, there are quarks and gluons and electrons and everything on this side, but there is no quark in this side. So the quarks got confined inside or caged inside protons and neutrons, and that's the confinement. So that means below this microsecond or at the microsecond old universe, it must have been in a deconfined phase, which we need to study in the laboratory. Now, conceptually, there are two ways extremely that you can reach there. One is, of course, by heating. That means you pump up a lot of energy and there will be a lot of particles produced. And then you will get a soup of quarks and gluons where everybody will kind of lose their identity where from they have come from, which has a similarity with early universe. And another one is compression. That means you compress in such a way that inside one proton, you might have 3 or 4 protons in the same volume. And then also you will reach here, which is having a similarity, which is at the core of neutron star. Now, the way we study the whole field of physics, as Dr. Mohanty also showed, is that we have a phase diagram where there is a net baryon density, which, as I said, is highest for the neutron star, almost temperature is 0. And then there is the temperature axis. And these are the different laboratories, namely relativistic heavy ion collider, large hadron collider, which essentially pumps up the energy to high and then gets a system which is at very high temperature and very low density. And there is another one, which this was the GSI, which is so, I will come back to that later, which might reach there. Now, this phase diagram I saw essentially when I started my career, maybe 3 decades earlier. Now, the phase diagram, if you look today, this is how it looks like. In the sense So there is already a point which has been put together, and then I think it is agreed upon that there is a phase transition which is crossover. There is no hint of critical point yet, but then this place has become very crowded. It was just one line and there was almost nothing. So there is a colored superconductor, there is a quark-ionic phase which is in between the quark-gluon plasma phase and the hadronic phase, and of course there is a neutron star, and then there are all sorts of things that are there in the theory. So the point what I'm trying to make here is that, yes, this is very important, this is going on. This is the one which has drawn a renewed attention to the community. And this is obvious from the number of experiments which are coming up since then. As you can see, there is star. Bedanga has said that there's a star beam energy scan. They started with 200 GeV, they have come up to around 7. There is a fixed target which even go up to 3 GeV. There is a Nika in Dubna, which is supposed to come up. There is the SPS CERN, which is NS61 and SINE. There is the Hades, which is running at GSI up to 2 GeV. And this is the one which I am going to talk about, which is compressed baryon emitter experiment, which will be at FAIR facility. And this is my connection to this physics of building FAIR, because there is a renewed interest in high density nuclear matter, which I am going to discuss here. Now, this is the beginning. In fact, it's not the beginning, but it is some kind of, you can say, end of discussions, which is on 7th February 2007, where there is a signing between two ministers, our Minister of Design, Science and Technology and his counterpart in Germany, where they said that India will contribute up to 3% in building this facility, which is called FAIR. Now, where is FAIR? Many of you might not know is that now if you go to the road, means from Frankfurt Airport, this is Frankfurt Airport, and there is a road and there is a small village called Wixhausen, and there is a road called One Planck Street, that's the name, and there is a laboratory named GSI, which in Germany in English called Heavy Ion Facility, which is existing for more than 40 years. And this is the laboratory which is credited with discovery of 7 periodic table elements, including Darmstadtium, where it is situated. And then they decided to make it an international facility, and this is what is FAIR. So these are the elements which are there, 7 of them: borium, haitium, meitanium, Darmstadtium, rongium, and copernicium. But then this is how the FAIR conceptually look like. This is what is existing GSI. And this is all colored one is supposed to be the part of the FAIR facility as it has been seen or conceptualized at the beginning. So beam will come from here. There will be some acceleration here, which is existing. This is called CIS 18 Tesla meter. And then it will be accelerated in a ring called CIS 100 and 300. It's the same ring. Depending on the magnetic field that you will pump in, you may get 100 or 300. And then beam will go delivered to different facilities. Now, the uniqueness of FAIR is not that it is only a particle physics research, but it has some other physics reach, which I will discuss. Now, India is the 3rd largest contributor after Germany and Russia. Another feature is that it is not a high energy machine. It will essentially go up to 45 GeV maximum for ions and in the last phase. But more importantly, it is a high intensity machine. It will have 10,000 times higher intensity in primary beam, 100 times in radioactive ion beams for nuclear physics research. And of course, there will be 4 parallel operations in FAIR. Now, India has been contributing in two aspects. One is accelerator equipment, another one is doing experiment. In accelerator equipment, we are supposed to deliver 678 of power converter, ultra stable, for both for the magnet, superconducting and normal conducting. 339 have already been shipped and it is accepted. We are supposed to deliver ultra high vacuum chambers of 71 numbers, 58 have been shipped. And there is a device called beam stopper, which essentially stops the uranium, high intensity uranium beams. So this needs a huge, very delicate design and building. 3 units of them. The design is over, purchase order has been issued. And there are coaxial power cables of 194 kilometers. There are signal cables of 16 types, and of course there are shielding. And there is the design of superconducting magnets. These are our pledged contributions. Now this is the power converter. This is the picture. You see, we have to build 680. This is 1 unit. Like that, it is the picture has been taken in ECIL, Hyderabad. They have built it. And this is the picture in Germany. So these are our power converters which are lying there in their storehouse. These are the vacuum chambers. This is built by a company in Bangalore nearby called Vacuum Technique. And this is in their factory. All the vacuum chambers are ready to be shipped. And this is when it reached Germany. So these are the equipment they have been already supplied. And this I want to make a little bit better mention of that, because this is a device where uranium beam, if it falls, then it will deposit all its energy here, and it will essentially like an explosive device. So you have to have proper cooling for that. And this design has been done completely. It was not existing by a lab called Central Mechanical Engineering Research Institute, Durgapur, which is a CSIR lab. Now I come to the FAIR physics. FAIR, as I said, unlike any other facility, will essentially cover the region from today till 10 to the power minus 6 or close to that. Now, this is the one which is said QCD physics. That means there is an experiment called PANDA, which will look into the PP bar collisions and look at the resonances to understand the hadronic structures. And then, of course, our field of physics. Then there is a huge, because GSI is essentially a nuclear physics lab with radioactive ion beams, and then atomic and plasma physics research and applications, namely space and biophysics applications. Now, Indian community are involved in two basic areas. One is nuclear structure, astrophysics, and reaction. As you know, this is the stable nuclei line with N versus Z almost equal. Now, what will be covered in GSI is essentially this region where the neutron number is high. So these are all neutron-rich nuclei, which will allow you to study the halos, which is around the nucleus, neutron skin, and there are some very interesting resonances, and of course the side of the neutron star. And these are the cross sections, so it goes down as you go towards this, but this will be the specialty, and then we'll do experiments with this. So FAIR will provide unique access to many nuclei relevant in explosive nuclear synthesis. And this is the question that we will address. Yeah, so these are the detectors which have been built for nuclear physics experiment in VECC, neutron detectors which will be shipped to Germany. Now I come to our kind of physics. Now this field of physics, where it is high density, high baryonic density matter, has got a renewed interest after 2017, after the discovery of gravitational wave along with the electromagnetic signal. Now there have been a calculation by a GSI scientist, these are the authors and reference, which was done in 2010, which essentially says that luminosity of the elements which are produced and then it decays in a radioactive way. So what is the luminosity with time? So this is his plot, and these are the results after 2017, which essentially matches. So what we are trying to say here is that we are in that laboratory where two neutron stars merge, there is creating a system which is essentially similar to the one which we are studying in the lab. So there have been some more calculations. This is the calculation, this is the reference for neutron star merger. And you see this is the density, which is around 3 or 4 times the nuclear matter density of the core. And this is the temperature, which is around 10 MeV. This is what is the neutron star merger. And this is what is the heavy ion collisions at 1.58 GeV gold-gold collisions in semi-peripheral. So this is the density again, which is about 3 times the nuclear matter density. And this is the temperature, which is a little bit higher because this is like 90 to 100 MeV, not like 10 MeV. So what is the connection between these two? The connection is essentially the equation of state. If you can understand the equation of state here, we can certainly apply here. If you can understand here, we can test and see how it looks like. This is the experiment. That is only one experiment that is being built at FAIR for this. The name of the experiment, compressed baryonic matter experiment. It's a fixed target experiment, unlike ALICE, which are collider. And this one important thing here is this is a facility, as this is one experiment. So the main idea is to detect in full glory the dielectron signals, both dielectron as well as dimuons, so that we can understand the invariant mass. We can change the study the change in masses or even chiral symmetry restoration. So this is the ring imaging Cherenkov counter, which is for, this is the magnet and there is a silicon detector. And this is the device which we are building. This is the complete device. The way it will take data in 2 modes, this guy will go away and this guy will take in and maybe take 6 months data, or then the other guy will come. So it is either in dielectron mode or in dimuon mode. So what is there in dimuon mode detector? So we have to understand something with 10 megahertz collision rate, which is unprecedented, never happened. We have to determine the vertex with 50 micron accuracy. We have to identify both electrons and leptons and hadrons. Can someone? Yeah, okay, thank you. Okay, so another important thing is that as the collision rate is very high, we cannot have the luxury to ask for trigger and take the data. We have to have a free streaming with a timestamp associated with the signals, and then you collect them and do in computer all the reconstruction. So that is why it is called 4D. Now, what we are doing in India, we are building this whole device, which is having the absorber, which will absorb the hadrons. Unlike a single absorber, this is called segmented absorber, and there will be chambers of detectors which will essentially track the muon passing through this. And there is a silicon detector which will essentially give you the momentum. Now, the challenge is that this will handle like something like 400 kilohertz per centimeter square. These guys will 130 kilohertz per centimeter square. And this is how they will look like. So not all detectors will do the job. So we have been working in VECC for development of this kind of detector called GEM, gas electron multiplier, which has been tested to work up to 3 megahertz per centimeter square. This is nothing but a gaseous chamber which works. The amplification happens in a foil, which is the polyimide foil with 30 micron, 50 micron thickness, and there are 40 micron hole, 140 micron, 70 micron dia hole, 140 micron as pitch. And so when there is an electric field around this, then the electron get multiplied. If you make a cascade, then you won't have to put a lot of voltage in that. So this is the advantage. This is in our lab. They have been put together, and this is one GEM chamber, full size for the experiment. Now, before FAIR starts operating, there have been one phase called phase 0, where all the detectors which will come in CBM in their small form, like we have put 2 chambers, instead of that we will have 130 chambers, have been put together to a beam which is nickel, nickel and gold, gold with 1.23 or 1.93. And this is the structure of the beam. This is when the beam is on. This is on spill, this is off spill. And these are the two, our detectors, GEM1 and GEM2. And this is the detector built by Heidelberg University called time of flight. And this is the time correlation, which is fantastic. This is a spatial correlation, which also looks nice. So that means the detectors work. Now I go to my final kind of slides where I show the status of the facility as of today. So this is how it would look like in 2017, where all the forests were essentially cut and the place was made. Then there are a lot of problems in the sense there are regulatory restrictions which has increased, and so the project got delayed. And this is what is the existing GSI. And this is how it looks like today. So all the tunnel is ready now. This is a 60-meter wide and 20-meter deep tunnel. There are two, this will house both CIS-100 and CIS-300. This is GSI, there is a connection of beam coming here. And this is the tunnel from where the beam will go from CIS-18 to CIS-100. It will essentially stair and going down. And this is the main tunnel where all the magnets and other equipments will be stationed. And this is the other buildings which are being built now. This is a very busy place if anybody visits the place now. And this is our experimental hall, which is ready. So if you want, we can start installing our equipment there once the services are all ready. This is how it will look like when everything is ready. FAIR is in its full glory, so everything will be underground. You have to get back your forest back because that is how the arrangement is. And of course, this is the GSI, and this is where all the experiment will happen. Now, like many other large projects, this has also gone through its own problem. It is delayed first, as you said, because of the regulatory restrictions, and then recent international events involving Russia, because Russia is 18% contributor to the whole 3 billion euro project. So one can imagine that what will happen. And so now the expected beam was in 2018 initially, then in 2024. Now the date given is 2027 somehow in Cuttle version, but let's hope things work by then. So this is where FAIR will explore a range of physics goals, including strongly interacting matter under extreme density, nuclei under extreme conditions of neutron by proton number. Indian participations includes key accelerator equipment and advanced detectors. And we hope to overcome various issues soon and start taking data. Before ending, this is my last slide. What happens? It's not showing here, it's showing here. Anyway, I am just reading it. This is basically a new pack recommendation. Yeah, this is a new pack recommendation, which was in 2017. It says FAIR is a European flagship facility for the coming decades worldwide. Unique, it will allow for a large variety of unprecedented forefront research in physics and applied sciences. It focuses on the structure and evolution of matter. Its multifaceted research opens a new era in our understanding of the fundamental building blocks of matter and the forces as well as the evolution of our universe. The new possibilities for research in Darmstadt are unique and are expected to produce groundbreaking new insights for nuclear research. I believe this is relevant even today. Thank you.
Thank you, Subhashish. Let's have some questions.
Are there at least some things that can start before this projected? I mean, not maybe CBM,
Yeah,
but the low energy
I'll tell you.
experiments?
There is CIS-18 which is running.
Okay.
And so far as nuclear physics research is concerned, they can do good bit of it using CIS-18 because there is a fragment separator already existing, not the superconducting one. But the problem is that the yield of those means neutron-rich nuclei are so low that you have to wait along. So that research is going on. That is a part of phase 0. And so far as CBM is concerned, we are running at 1.2 GeV. We cannot go beyond that. We can test all our detectors with that, and maybe with some particles like lambda yield and others. That is being done. Yes.
Okay, let's thank Subhashish again. The next talk is online by Dr. Vaishali Naik from IISc. She's going to talk on India radioactive beams.
Good afternoon, everyone.
Good afternoon. We're
I'll
just
just share my screen.
We're just setting up your talk. Give us a minute. She's ready. So can you please share your screen? In full screen mode, please.
Yes. So are the slides visible?
Yes, and that is fine. So you can begin.
Yes. Okay. So first of all, good afternoon, everyone. At the outset, I would like to thank the organizers for inviting me to speak here today, particularly Professor Rohini Godbole and Professor Amit Roy. I really miss being there physically, but it's thanks to the organizers for arranging for this online talk. So my previous speakers, they have already given an overview of the mega science vision exercise that started about 1.5 years back among the nuclear physics and high energy physics as well as accelerator physics community. So in my talk, I will be focusing on the radioactive ion beams related activities, the vision, challenges and opportunities that we envisage in coming a decade or a decade and a half or so. So this, the Mega Science Vision document, which outlined the core areas of research and development that the community would like to focus on, is shown here. So for the nuclear physics, it is investigation of the structure of nuclear matter at the extremes of isospin, angular momentum, as well as other aspects of in the field to understand the various reaction mechanisms for production of super heavy elements and nuclei away from the line of stability. So the major recommendations which are part of this mega science vision document are to develop new accelerator facilities within India for radioactive ion beams, high current stable beams, and underground laboratories for the low energy nuclear physics programs. Also, augment state-of-the-art detector systems at the existing accelerator facilities, which is essential to cope with the developments in the field. And of course, we shall continue strong participation in the experiments at FAIR and other international nuclear physics laboratories for radioactive ion beams as well as photon beams. Experiments using these facilities. So, as many of you or all of you might be aware that physics with radioactive ion beams is the new frontier in nuclear physics and allied sciences now. The main motivation is study of exotic nuclei, which is nuclei away from beta stability line. So here I have shown the Segre nuclear chart, where the neutron number and is plotted on x-axis and proton number on y-axis for all the nuclei that are predicted to exist within the limits of particle stability as defined by the neutron tripline and the proton tripline. So about 300 stable nuclei exist, shown as black dot on this nuclear chart. Around 3,000 or so radioactive nuclei have already been produced using the heavy ion facilities as well as the first generation radioactive ion facilities, shown here in yellow. And the gray region shows the nuclei which are predicted to exist but not yet studied. So these exotic nuclei which have been studied so far, already we know that show very unusual properties, very different than the that shown by nuclei close to the beta stability line. And also several of these nuclei away from stability lines participate in nuclear astrophysics reactions such as rapid proton capture as well as rapid neutron capture. So there is a great interest for nuclear physics related data for nuclear astrophysics related questions. So that's why need for systematic study of a large number of nuclei for the refinement of better predictability of nuclear models. And that is mainly the prime motivation of radioactive ion beams. The advantages is that large number of and as well as different large types of species of beams will be available. And because radioactive ion beam itself is either neutron rich or proton rich, the exotic nuclei which are closer to the drip lines are expected to be produced with better signal to noise ratio. I have just listed 3 phenomenal discoveries that are driving the field of radioactive ion beams. The neutron halo, where basically discovered by Tanihata et al. At Berkeley, where the extremely neutron-rich nucleus of lithium element, it shows the size, matter distribution, and unexpectedly large, almost same as that of lead nucleus. Also, as one moves away from beta stability towards the drip line, new magic numbers such as 16 or 34 start appearing, and there is also weakening of shell structure. And of course, the RIB facilities remain an engine of discovery of new elements. Currently up to Z is equal to 18 element has been discovered, and also new isotopes. For example, at RIKEN, in one experiment, 45 new isotopes were discovered in the RIBM factory project. RIB is also a very potent tool for research in applied sciences, because now one has an implantable radio tracer, so one can implant also in chemically incompatible lattice. Also, industrial scale radioisotope harvesting is being planned. In fact, the MEDICIS facility at CERN from spent targets as well as beam dumps. And also a new area is emerging where the possibility of using radioactive ion beams in particle therapy, like carbon therapy, future carbon therapy is being studied. Here the advantage is that if one can use the low half-life PET emitters such as carbon-10 or carbon-11 or oxygen-14, then it enables in situ dose mapping and improved treatment planning because of the in situ PET scan available. So this is an emerging area of R&D, which is so no wonder that almost all the major accelerator laboratories in the world have built RIB facilities and also currently building the next generation, much more powerful facilities. So at this moment, the operational most powerful facility is the RIKEN RIBeam factory, having a cyclotron park, having 3 cyclotrons and maximum energy of up to 350 MeV per nucleon for uranium beam. And first, of course, RIB facility was built in Belgium. And FAIR, my previous speaker has already given a nice overview. ISOLTE at CERN is the largest ISOLTE RIB facility. Spiral 2 is the next generation RIB facility in France, Ariel in Canada, and also EFRIC in USA, MSU. So here, this ISOL and IF means in-flight separation. So basically, these are the 2 modes of producing RIB. So in isotope separator online method, basically the primary accelerator and RIB accelerator, they operate simultaneously. That means the primary beam, which could be a light, low energy beam or high energy heavy ion beam, is stopped in a thick target, and radioactive atoms diffusing out of the target are transported to an ion source where they are ionized, mass separated, and then the RIB of interest is accelerated to the desired energy. So in this method, one gets high beam purity quality, but obviously because of the ion source and target related delays, it is element dependent, and half-life limit is typically greater than 1 second or so to get a reasonable intensity. Whereas in the infrared separator method, one starts with a powerful high energy heavy ion beam, which bombards a comparatively thinner target. So here the projectile itself gets fragmented, and the projectile fragments moving in forward direction, retaining the velocity of the primary beam, are separated in a powerful in-flight separator. So one does not need a post-acceleration or an ionization stage, and one can get a very high energy beam at the output of the facilities. So no half-life limit, but because isotons cannot be separated, and generally one has to have a reasonable momentum acceptance for the separator to get the intensity. So lower beam purity and quality is the problem of this facility. But these facilities are the much sought after facilities for producing and identifying new isotopes. So coming to the plans and the RIB facility that has been already developed at IISc, this shows the block diagram. So we take the beam, primary beam from the K130 cyclotron, which bombards the target, and using the gas jet recoil transport method, the activity is transported to ion source, charge breeder, then mass separated, and then followed by radio frequency quadrupole LINAC and other TTL heavy and LINAC modules. This facility has been built at our current campus, and the purpose was to complete all the R&D steps for individual building blocks towards the next generation RIB facility, which is called Anurid. This stage is essential because the development of accelerators for radioactive ion beams, the ion source, etc., is highly R&D intensive, and one has to develop one's own blueprints. One cannot just go to the market and buy a RIB. So currently the facility till LINAC third module with an output energy of 415 kV per nucleon has been commissioned, and the next stage has been installed, and we are now working on the commissioning the high energy beam. For Anurip, which is planned at our new campus at Rajarhat, the primary accelerator will be superconducting electron linear 50 MeV and 100 kilowatt CW, as well as creating neutron-rich nuclei through photofission, and also a proton accelerator for getting neutron deficient radioactive ion beams. This is because the intensity of radioactive ion beams is very dependent on the higher intensity of the primary beam. So higher the intensity of the primary beam, higher will be the intensity of the radioactive ion beam. So that is the reason we are planning these accelerators for the Anurip facility. So at this moment, Calcutta, IISc, we have 3 operational cyclotrons. The room temperature cyclotron, operational since June 1977, is the machine which we are using for nuclear physics experiments, as well as this is the primary accelerator for producing RIB. Of course, the superconducting cyclotron, the beam commissioning was done in 2020, and now highest energy neon and oxygen beam are available from this facility. So this is also going to be available to the nuclear physics users and other users. And of course, the medical cyclotron facility, which is for societal applications and commercial radioisotope production. So the RIB facility, this shows a photograph of our facility, which is installed in one of the old experimental caves of the K130 cyclotron. So this shows the radio frequency quadrupole LINAC, the buncher and MEBT, and first two linear accelerator modules. The list of beams that are accelerated in our facility so far is listed here. So oxygen 14 having a half-life of 71 seconds, indium 111, 2.8 days half-life, and typical intensity, highest intensity that we get is about 10 to the power 5 particles per second. And beam energy after RFQ is 1.4 MeV for the oxygen 14 beam. Along with radioactive ion beams, the facility remains a very good facility for stable isotope beams, which are used by material science users. So these are the energies of stable isotope beams like carbon, nitrogen, oxygen, argon, etc., which are available from the facility. This shows some technology milestones. The ECR ion source, radio frequency quadrupole LINAC, heavy ion LINAC, all developed, designed and developed indigenously and fabricated in the country. Also, in international collaboration, via international collaboration, superconducting cavity development we are doing. So this is a photograph of Indian institutions Fermilab collaboration, low beta 650 niobium cavity that has been fabricated at IISc, EB welded at IISc, and also tested at Fermilab with very good high acceleration gradient was obtained. This shows a photograph of the injector cryomodule for the superconducting electron LINAC and a QWR heavy and LINAC cryomodule with hermetically sealed cavities, which is basically the technology development for Anurip facility. And a photograph of our collaborators, RIKEN for physics design of accelerators, exotic nuclear physics, Samir Mumbai, who have developed all the RF transmitters for the RIB facility, CMRI Durgapur, who have fabricated the radio frequency quadrupole and some other accelerator components, and Triumph Canada, with whom we are collaborating on the development of superconducting electron LINAC and QWR heavy ion LINAC cryomodule. This shows the photograph. And now when we started thinking of the launching the work on Anurip facility, that time an international advisory committee was constituted. These are the members of the committee, chaired by Nigel Lockyer, Professor Swapan Chattopadhyay, Yasushiri Lianusan from RIKEN, Leah Marminga, Andrew Hutton from Jefferson Lab, Matt Andrews, and also Professor Amit Roy, Professor Kailash, and Dr. Alok Chakravarti, who was our team leader for radioactive ion beam facilities and program, and also Professor A.K. Sinha from university side. So this International Advisory Committee gave a very favorable report, and that helped us in getting the confidence of going ahead with the Anurip project. Also, the science opportunity workshops were conducted called SCRIBE, which is Science with Rare Isotope Beams. And this shows the photograph of one of such workshop. I can see Professor Chattopadhyay here, Dr. Alok Chakravarti, Nigel, Via, and Kubo-san from Riken, and my other colleagues. So this shows a schematic of the Anurip facility. So what we, as I said, so there will be two primary accelerator, a superconducting electron linac of energy 50 MeV 2 milliamperes, and a proton cyclotron of 50 MeV 200 microamperes, bombarding two separate targets, where respectively neutron rich and proton rich RIB can be produced, and the scheme that I showed earlier of isolated RIB facility. And experiments opening up at low energy with RIB as well as stable isotope beams, as well as in phased manner, one can start the experiment at medium and high energy. And eventually at about 5 MeV per nucleon or so, the beam can be injected in a ring cyclotron to get a high energy beam of about 100 MeV per nucleon. So at this moment, the status, as I mentioned, is the low energy RIB facility is built, and now we have the blueprints of the facility up to the LINAC module. Pre-project activity is ongoing. Site clearance from regulatory agency, building design, R&D on gap areas like superconducting electron linac and high power actinide target development is ongoing. Anurip is planned to be constructed in phases. Approximate cost is about 1,000 crores. Of course, I must add that these are pre-pandemic costs, so likely to go slightly higher now. And timeline is that we have funding till March 2024 to complete the detailed project report and the R&D that is ongoing, and submit the project report to the funding agency by March end 2024. And for construction, our estimate is that it will need about 10 years and about 2 years for beam commissioning and first experiment from the facility. So this shows a master plan of Rajarhat campus. So the Anurip site, the building size is approximately 100 meter by 200 meter. This is a greenfield campus, 25 acres size. At this moment, some of the facilities like multipurpose engineering hall, guest house, AMD ARB building, as well as RMRC, which is a radiation medicine research center, is already operational. And Anurip facility site, of course, as I said, the geotechnical investigation and other things that are needed for regulatory clearance are in advanced stage. So this is now mostly the end. I'm towards the end of my presentation. Just to say a few words about the other area. Yeah. So this is already covered by Vandana Nanal, but I just wanted to say that presently the nuclear physics community uses mainly 3 accelerators in India. That is the VECC and the 2 Pelletrons and TF1 and IISc. And of course, the facilities have been listed in the mega science proposals. And just 2 minutes. Just one another point I wanted to add, that BRC also is planning for a proton driver-based RIB facility at the new upcoming campus at Vizag, Visakhapatnam. And although it is planned for 1 GeV, they plan to start as soon as the 50 MeV low energy proton beam is available. So this is already covered by my previous speaker, Subhashishta. So I'll just skip and just summarize that low energy RIB facility and work on next generation RIB facility is ongoing at PCC. The development is well aligned with the Mega Science Vision 2035 recommendations put forth by the nuclear physics community in the country. So this is all I had to say. Thank you. Thanks for your attention.
Thank you very much.
Yeah.
The talk is now open for questions. Yes, please.
I have two small questions. One is that you showed a timeline of about, I think, 10 years, right? After the t equal to 0, after you get the funding.
Yes, yes, Professor Datar.
Yeah,
Yeah.
at what stage is the 10 MeV per nucleon facility done? And that's one question, and maybe I can quickly ask the other one as well. That isn't it true that the space that you have provided for experimental halls and so on is limited? So is the plan that you will go down or up, build another floor or something for other experimental facility?
No, so let me answer the second question first. The building of 100 meter by 200 meters. So the experimental halls and caves design has been made in consultation with the nuclear physics group at IISc. So we feel that in the same floor itself, the experimental facility and halls should be sufficient. So that is the first answer. And second answer is that for 10 MeV per nucleon, at the current site, we will not be able to go to that higher energy because of space limitation. For the entire facility, at least we have assumed that for building construction, we would need about 4 to 5 years, and considering the current limitations in our country. So construction of the components for the accelerator will going on in parallel. And as soon as the building and services are handed over to us, we will start installing the facility. That is the thing, because until and unless we can do some parallel processing in terms of implementation strategy, we will not be able to meet the 10 years timeline. So Professor Datar, I hope I have answered your question.
Yes, yes, that's what he says.
Yeah.
Thank you very much. Let's thank Dr. Naik once again. And let's call on the last speaker of this session. That is Professor Datar himself. India Underground Experiments Review.
Okay, so let me first of all thank the organizers, Swapan and Rohini, for this opportunity to speak before you, and also, of course, the hosts, ICTS, for the wonderful, ambience and so on. Okay, so I'll be building on what Indumati has already said, but hoping that we will have an underground lab somewhere deeper, and what will we do with it? Yeah, so this is the plan of my talk, some background to underground research in India, the need for an underground lab and some experiments that we have been thinking about, and the future outlook. Okay, so underground research started in about 51, a few years after Homi Bhabha founded TIFR in Bangalore, and he got Professor Srikantan to begin a series of experiments in the Kolar gold fields, and that was to measure muons with the detectors that were then current at that time. So using the rock density, he measured, this group measured the muon flux as a function of depth, and then that could be converted, knowing the rock density, to a cosmic muon spectrum. So these are some photographs of the deepest mine in India, the Champion Reef mine, some of the detectors that were used to measure muons, and on the right, lower right, is this picture of the proton decay detector with Nava Mandal somewhere. Yeah, okay. So this collaboration over the years produced the most comprehensive depth versus muon intensity curve. And as you can see, this extended over several orders of magnitude. And at some point, they hit a flat dependence, which showed that these neutrino experiments could be done. Okay. So the first atmospheric neutrino detection was done in 65 in KGF. And this is the paper. So it was a TIFR, Osaka City University, and Durham collaboration. And interestingly, this paper came out on the 15th of August, or Independence Day in 65. Of course, simultaneously, atmospheric neutrinos were also, evidence for that was found in a South African mine by Reines and his group. And that paper came out about 2 weeks later. Okay, so coming to more recent times, a small underground lab has been working in the Jaduguda mine. Interestingly, this is a uranium mine. So one would say, okay, why are you doing underground experiments in a uranium mine? But the thing is that this uranium mine has been working on ore, which is just about 500 ppm, plus or minus about 100. So nobody else in the world would ever do such things. But we did not have access to uranium. And so this is the only place. So Baba supported this activity so as to support the reactor program. Of course, now we have better sources of uranium in the country, and also because of this nuclear agreement and so on, we can get it from elsewhere. Okay, so this lab is at about 550-meter depth. You can see this here, 555 meters. The muon, fast neutron, slow neutron, and gamma ray backgrounds have been measured. And interestingly, an experiment has also been done by the VECC group. And this shows the group here looking very happy. They've actually done an experiment which contradicts their earlier result, which had a problem with the cosmic ray pileup, and they attributed it to fission fragment Bremsstrahlung. So this was a measurement of gamma rays in the energy region 25 to 80 MeV in the spontaneous fission of 252 Californium. So the earlier result was somewhere here, and there were other groups elsewhere who had also done this. But when they went down, the muon background came down, and the muon pileup, of course, reduced drastically. And so they contradicted the earlier result of the same experiment by the same group. Okay. So this is just one example of experiment done at that place. So now I come to need for underground lab, possible experiments. Many experiments which involve neutrinos, rare decays, ultra low cross-section measurements are finally limited by the cosmic ray background. So this is, of course, needed, such a lab. And some experiments, of course, can be done at a few hundred meters depth. Some of the nuclear astrophysics experiments can be done. But some others require the largest possible depths. For instance, experiments like the SNOW experiment, which actually measured the neutral current signal through singles measurement of neutrons. That requires that the muon flux go down a lot. Otherwise, you would mistake a neutron signal for actually a muon-induced neutron signal. And then, of course, there are many seismic measurements that also require deep sites to reduce noise. Indeed, there is also a gravitational wave detector being built by the Japanese in an underground site called Kagra. So there are many possibilities once you go underground. I don't know whether this is, yeah, it has. There's a big delay, yeah. The experiments, so there was a expression of interest meeting about 3 months ago in TIFR, where various groups were called. Of course, not all groups could come at that time. So I will talk about some things that those groups actually were not able to make it in that meeting. So broadly, these experiments involved neutrinos, dark matter searches, nuclear astrophysics, rare nuclear decays, and geophysics. Again, maybe in future, we will also get the biologists on board, because some experiments of that sort also can be done. So the experiments involving neutrinos, of course, you have heard about the 51 ICAL detector for INO, what are the physics that it can do. I will also say a little bit about solar and supernova neutrinos that can be done with something that we have been working on starting about a year ago on a 1 kiloton deuterated liquid scintillator. The neutrinoless double beta decay, I think Vandana just alluded to, because she was also talking about other kinds of detectors. In 124 tin, that's an ongoing R&D. Dark matter search using both cryogenic cesium iodide and then cryogenic silicon, superheated liquid, and so on. I will not talk about that. So the ones in blue, I will say a little more about. Nuclear astrophysics, there's a group formed involving universities, IITs, and some of the research institutions, who want to put together a low energy accelerator of the order of 5 million volts, single-ended, underground, and also develop a supersonic gas jet target, because these things involve very high beam currents, and also a recoil mass separator. All these things are some things which the low energy nuclear physics community is quite familiar with. So these are things that are not terribly unknown, but they do require some developments like this gas jet target and so on. Okay, then there are also proposals to measure rare nuclear decays, forbidden decays, and so on. Because of these other experiments which involve very rare events, you also require a low background lab. This is something that Vandana already talked about, and such a thing should be there in an underground lab as well. And then there are geophysics experiments, which involve seismic measurements, gravimetric measurements, geomagnetic, and radiogenic experiments. So the ones in blue I will talk about a little more. Okay, so this is something that we want to do, and this would require a deep underground lab. I don't know whether I've skipped a slide. The need, wait a minute. There's some slide which, yeah, okay. So, okay, well, so we for some experiments, as I said, we require 2 kilometer rock overburden. Okay. Okay, so this low energy neutrino detector would involve a deuterated liquid scintillator. This is, of course, inspired by the Sudbury Neutrino Observatory experiment, which is a seminal experiment. And that used 1 kiloton of heavy water loaned for $1 by the company that makes this heavy water. And they measured the solar neutrinos and solved the solar neutrino problem in a beautiful manner. Now, what they did is to look at the Cherenkov light. And for the neutral current signal, of course, they had various phases. And the last phase involved putting helium-3 counters to measure in singles the neutrons that are produced as a result of neutral current interactions. But the threshold for the neutrinos was of the order of 5 MeV. Note that. This is also roughly the threshold that is there in the Super K experiment, the 50 kiloton water Cherenkov experiment. A deuterated liquid scintillator, just because the light output is much, much more than in Cherenkov, would have a much lower threshold, possibly 100 or few hundreds of keV. So that would lower that very much. And the other thing about the deuteron is because it's a loosely bound proton-neutron system, it can measure through the charge current interaction both neutrinos and antineutrinos of the electron type, essentially, because this is a low energy detector that we want to build. So these are the reactions that are involved. The neutrino and the antineutrinos of the charge current, these are the thresholds, energy thresholds. And as you can see, the neutral current is again, you can do it for any kind of neutrino, nu e, nu mu, nu tau. And the threshold is, of course, the binding energy of the deuteron. And you can, of course, measure also elastic scattering on the electron, but also elastic scattering from the other kinds of neutrinos. So this is a very versatile kind of neutrino detector because of the fact that it has neutrons and protons and electrons, where you can determine elastic scattering. Okay, so what science can a 1 kiloton DLS, stands for deuterated liquid scintillator detector do? So one of the things that it can do, for instance, is to measure the survival probability of the electron neutrino over a large span of energy. Now, what has been done by Borexino is in this region below about 1 MeV using the 7 beryllium neutrinos, and at the higher energies of the order of 4 MeV or so, 5 MeV or so, 5 MeV and higher, so the average energy is about 8 MeV or so, by SNO as well as Super Kamiokande. Now, what such a detector could do just in 1 year, this is an estimate, is that it could put a point here. And in fact, with more data, you could actually fill up that intermediate space. Now, that would enable you to distinguish between the so-called MSW paradigm, which is the currently accepted way you analyze things for solar neutrinos, but also distinguish between other non-standard interaction theories beyond standard model theories. The other thing that this could do is that it could measure the day-night effect. This has been measured to 1 to 2 sigma level by SNO and also by Super Kamiokande, because they're actually looking at the tail end of the neutrino spectrum. If you can measure it for lower energies, and in fact for the whole spectrum, we think we can do it much better. Of course, how it started was we looked at the possibility of using such a kiloton DLS for supernova neutrinos. So this is the reference for that. we could look at supernova neutrinos and antineutrinos, and those from supernova are typically 10 MeV and higher. This is a very good detector for that. We can, of course, signal the appearance of the supernova like other detectors. So you could contribute to the supernova watch. We could help in the multi-messenger astronomy. And as Amol and Dasgupta have shown, that you can also infer the mass ordering and new interaction signatures. Now, why DLS? Because India is best placed to do that. We are the largest producer of heavy water in the world because we have heavy water-based reactors, nuclear reactors that produce power. In fact, I think it was about a year ago or a little more than a year perhaps, that the government approved the construction in a caravan mode of 10 700 megawatt heavy water-based reactors. So the Heavy Water Board has the capability to support that activity. And each reactor needs about 500 tons of heavy water. So they are geared up for 5,000 tons. What we require is about 1 kiloton. So they are not terribly perturbed by this figure of, when we asked them, we said, okay, can you do something like a few hundred tons? So they said, no, there's no problem at all. Then we said 1 kiloton, yeah, we can do it. So I think they have the capability of delivering this amount of heavy hydrogen. Now, of course, they can do it, but I mean, they can get you the source of deuterium. But of course, a lot of R&D is required to be carried out, and particularly in BRC, to convert this into the detector that you want. So on a small level of a few liters or maybe a few hundred liters or a few tens of liters, it has to be done in BRC. And then they can take over because they have the manufacturing capability. Now, the immediate goal we have, ideally, it would have been good to have a completely deuterated liquid scintillator, but that appears to be challenging. So what we thought is we'll first start out with a heavy water soluble liquid scintillator. There is already R&D going on. And so you can have something like, I mean, this is just a rough figure. So let's say a 95% deuterium heavy water with a 5% of hydrogen-based linear alkyl benzene, which is this main scintillator. And so, of course, the threshold will not be 100 keV, it will be about an MeV. But that's okay. You still are improving on the earlier threshold. So there are two groups have been formed looking at the science case as well as a group trying to develop this water-soluble liquid scintillator, deuterated liquid scintillator. Okay, now I come to another. How many minutes do I have? 5. Okay, so this is related to possibly a futuristic thing that in such an underground lab, one could also have another kind of detector, an indium detector. This has been for solar neutrinos. This has been proposed by Raghavan way back in 1976. And he even did, there is a group formed called the Lens Group. And the final thing that they said is that they would like to build a 8% indium loaded 125-ton liquid scintillator with a photon lattice, and a prototype of that is there actually built by Virginia Tech and placed in a mine nearby, the Kimballton mine. Now, this kind of segmentation is required because indium is actually a radioactive nucleus. It has a long half-life, but you require to reduce the random coincident background by a huge amount, by 10 to the 11 or so, and that is why it is necessary to do this. Booth explored the possibility of measuring quasi-particles in the superconducting indium, but it didn't go very far, at least as far as I know. Another possibility is using a cryogenic bolometer of indium metal, which would reduce the size from 125 tons to just 8 tons, and the size would be reduced from about 5 meters to about 1 meter or so. And this could provide, apart from a real-time measurement of the solar neutrinos, a line measurement where there's a one-to-one correspondence between the measured spectrum and the neutrino spectrum. It could provide an independent measure of the temperature of the sun's core using the shift and broadening of the 7 beryllium electron capture line, as well as the PP spectrum. Okay, so this is the transition. I will skip that. If there is a question, I can come to that. It basically involves measuring the electron in coincidence with the 2 gamma rays, or a conversion electron and a gamma ray, and a delayed signal. And that's how if you pixelize the detector. So this is the kind of spectrum which has been simulated by Raghavan. He showed it quite some time back when he came. He's no more now. This is the kind of spectrum that you expect from an indium-loaded liquid scintillator, a beryllium-7 line. Look, on the other hand, at the spectrum that you get from Borexino, which is one of the best liquid scintillators in the world. But that is a Compton-like spectrum versus the full energy spectrum that you get from an indium detector. Okay, that's the difference. So, for instance, they have recently published a paper where they claim that, I mean, I do respect their claim that they have measured CNO neutrinos, which are at the 1% level of the main solar neutrinos. And it depends on your ability to extract this red signal from this huge amount of background. So it depends on your ability to simulate and do various kinds of checks and so on. Whereas here you would actually just get a line spectrum. That's the beauty of this detector. Now, okay, I'll leave it at that. If there are any questions, I'll be happy to answer them. This is again a futuristic thing. Now, the nuclear astrophysics community in India has come up with a proposal to put an accelerator underground. And these are some of the cross sections that have been studied. But this is just to show you that there are many cross sections where the errors are huge, of the order of 60%, especially at the gamma energies which are of interest in nuclear astrophysics calculations. Because there are large extrapolations involved when you measure it at a higher energy, the cross section is large, but then you extrapolate down. And I will show you one example of a classic case. So these are some of the things that so you need cross sections at gamma energies, which are a few keV to a few hundreds of keV, depending on the charge of the two particles involved, the two nuclei involved, and the cross sections are very low. So it is not possible to measure them over ground. Sorry, this is the, oops, goes really fast. I want to go back. I should wait. Wait. This is the holy grail in nuclear astrophysics, namely the carbon-12 alpha gamma cross section. And there are many groups which want to do that. There is a group in the Jinping laboratory in China, which is the deepest in the world, 2,400 meters below ground. And they want to measure this using alpha beam on a carbon target. There is a German group which wants to do inverse kinematics. That is helpful in some ways because you can take a carbon-12 beam, shoot it on a gas target. And the main contributor to the background, which is this carbon-13 alpha N, which would be there in this approach. You see, this is the background and this is the cross section that you want to measure. So this will go away. But if you have a recoil mass separator, of course, this reduces very much more. So this is something that could be done. And so there is also a group which is has great expertise in building these recoil mass separator, design and building. And they want to do this. So they want to use a advanced supersonic gas jet target. They want to use a recoil mass separator to eliminate this background. And then they have also a very nice design for this. Okay, the other things that could be done is actually measuring radon. I think I do not have expertise, but apparently this is very useful in close environments. This would also give you signals of perhaps a seismic event that is about to happen and so on. So since time is short, I will skip this. There are also gravity, there is acceleration due to gravity that can be measured, anomalies in that. And there is this Wadia Institute of Himalayan Geology. So if this happens in the Himalayan region, which is where you would get these great heights, then these delta G's can be measured. And oops, this is terrible. I press something and then it skips, but when you want to come back, it comes slowly. Anyway, I'm near the last slide. So, for instance, they have these devices which can measure an acceleration of the order of 1 nanometer per second squared. Imagine, so we have 10 meters per second squared. So there's 10 orders of magnitude below that, and they have sensitivities of this sort. So, I mean, they have instruments which can measure this and which will give various kinds of new measurements in their view, and especially so in the Himalayan region. Okay, so the outlook is that we would like to have a tunnel-based underground lab with 1.5 kilometer rock overburden on all sides, as opposed to what we had in the earlier specification of 1 kilometer, and 2 kilometer vertically, and this would make it competitive worldwide. And then so possible sites are being explored given the situation in Thini. So let me thank and acknowledge all these members of the INO collaboration, NDBD, nuclear astrophysics, nuclear physics groups. Probably have missed out TIFR at BRC, seismology lab, radon lab, geomagnetism lab. And so finally, I come to the end. Thank you.
Thank you.
These are, by the way, pictures taken at this campus. Beautiful campus, as I said.
Thank you.
Yeah.
Quick questions. Maybe a question, not necessarily quick. Okay, let's thank
Okay,
Vivek.
good. Oh.
To him. Please go ahead.
Yeah.
So in these alternate sites that you have been looking at,
Yeah.
What is the most overhang that you have?
No, so the best site has about 2.07 kilometers. So that's second only probably to the Chinese site.
That's what I wanted
Because,
to
you
find
know, in
out.
the
How does
northern
it
region, as
compare
you
with
can
Jhumpi?
guess, I mean, these are big mountains.
So how does it compare with Jhumpi?
I do not want to tell you the site.
No, no.
But yeah,
I wanted to
because
have
that
a
is not yet
comparison.
finalized, but yeah.
No, I wanted to have a comparison
Yeah,
with Jhumpi.
So there are very good sites.
Thanks.
And also, I mean, other things are favorable.
So Rohini, do you want to? So
Huh? Yeah. Aruna, yeah. So yeah, I'm going to.
So
If there's-
there is a nice pleasant duty that has to be performed before we go for a coffee break. So I request you to be, yes.
Let's
let
thank
us
Vivek
the
first.
speaker again.
Because now
Thank
we are
you.
beginning the thank you process. So first, let's thank Vivek.
And now I
Okay,
hand over
thank you.
to the big thank you, madam.
So I'm going to invite Shrirup here on behalf of all of us to propose a vote of thanks. The reason we are doing that now is that most of the people who have been working tirelessly, after the coffee, they can go home and they need not wait for our panel discussion to be over. So Shrirup, will you please do the honors? Thank you. Yeah, so now I'll go out and I will go out and invite them.
It's always a pleasant duty, and it's a great pleasure to carry out this part of the program. So we are, of course, still looking forward to the panel discussion, to a couple of talks, and to the address by the PSA. But this is a good time to thank all the people without whom this workshop would not have been possible. So first of all, let me explain that, of course, this workshop has been conceptualized and organized by Rohini, Godbole, and Swapan Chattopadhyay. But some small part of the organization was also carried out by Amit Rai, Govinda Majumdar, and yours truly. And so we were the backroom boys, if you like. And so it is on behalf of all five of us that I would like to thank the people to whom it's due. So first and foremost, we are grateful to the ICTS, TIFR's International Center for Theoretical Sciences, and Director Rajesh Gopakumar for hosting this program in their beautiful campus. Thanks are also due to the Indian Institute of Science, and in particular to the Center for High Energy Physics and Chairman Justin David for co-hosting this workshop. We also thank the Chairman of the Atomic Energy Commission and the Principal Scientific Advisor to the Prime Minister for their support and encouragement, and we are looking forward to Professor Sood's address in a short while. During the organization, we received substantial help and advice from several people. I'll list them: Mike Peskin, Tauhan, Frank Zimmerman, he's here, I guess, Srinivas Krishna Gopal, and Purushottam Shivastav, who were sort of supposed to attend this, but I think they're traveling today, so they're not able to do it. Subir Sarkar and Subhashish Chatterjee, who is around, I suppose, for which I thank them all. I also thank all the speakers for coming here in person after a gap of maybe 3 years, and to the online speakers, some of whom had to wake up at unearthly hours to match our time zone. Also, all the members of the panel discussion, which is going to happen in a short time, and some of whom have come only for this. Thanks are due to all the session chairs for conducting the sessions and keeping the program more or less on schedule. I thank all the participants. It was a real pleasure to meet all of you in 3+1 dimensions. I also thank the online participants for staying with us, though in 2+1 dimensions, during these times when we are all suffering from online fatigue. We are also grateful to Srinvanti Chakrabarti and her team for their scintillating performance yesterday, combining an ancient dance style with a very modern theme in a very graceful and aesthetic way. Finally, I come to all those whose silent help and support has made this program so smooth and comfortable for all of us. So may I invite Rohini and Swapan to the stage for this part? Okay, but people won't be able to see you. Yeah, I'll just call him. Put them on the chair. So I'll first call the AV team who have been responsible for all that you can hear and see around you. So Naveen, Shantaraj, Gobinath, and Arun. Could you please step up? Yes. So without their help, you would not have been able to hear or see anything. And especially all the online stuff also, everything worked beautifully and smoothly. So please give them a big hand. Thank you. Yes. Now, all those who have done the traveling, let me call Basavraj. Is he here? So he has taken care of all our comings and goings. Difficult in a place like this. It's all done very beautifully by Basavraj. Okay. The guest house and the catering, who have been pampering us for the last 3-4 days, Mahindra and Suresh. Yes. And finally, the most important people who have run the program from the program office, Gayatri, Anupama, Raju, and of course, the person who has been interacting with all of us, Kavyashri. So please give them a big hand. Yes. And yes, please put your hands together once again for Kavyashri, because we have been all bugging her for a long time for small things. And last, but by yes, but last but not least, to the program.
For Kavyashri for heading the team
Okay.
so expertly.
All right.
So. And now last but not the least.
Last but not the least, the program coordinator, Aruna, who of course has handled everything with the.
She has ably led the team.
And the team.
So seamlessly.
Yes.
So thank you very much, Aruna.
So we are also grateful to all the support staff of the ICTS. That includes the cleaners, the waiters, the guest house attendants, all those, even the gardeners who have been able to do this. So please put your hands together once again for them. All right, so it's now coffee time. I won't take up any more of your time. Please enjoy the rest of the program and have a safe journey back.
Before you guys go, Rohini and I want to say something Sriru could not say because he is giving a vote of thanks. We could not have done it. We could not have done it without Sriru and Govinda and Amit sitting in the audience. These three really helped us out. Yeah,
thank you.
We cannot give you guys roses. Sorry.
Where are roses?
You don't get roses.
Okay.
You get discriminated against.
Yes.
So I join wholeheartedly with Swapan, and thanks to this whole team for making the last 4 days and all the arrangement completely seamless. No, there is nobody to take a picture, so it's on the camera, so it's caught by the camera, so they can take a still. Thank you again, and now we can all go and have tea and be back at 3:40. I think that was what we had said. So now what do we do? 3:45. No, the reason is that we are really. Okay, I'm only worried about many people wanting to catch their flights. And Ajay Sood at 6 o'clock. Yeah.
And get a good one. Yeah.
Tell all the people on the stage that tell them we are outside.
You want the RT card?
Yeah, I want RT
Yeah, yeah, RT.
If you have loaded, it's fine. If not, then I have a laptop.
Yeah, it's on. So